Year 13 short revision video number 14. So, we've got some information that we need to read through carefully at the start of the question. So, in an experiment, 500 fruit flies were released into an environment, a controlled environment. After 10 days, there were 650 fruit flies present. Munira believes that n, the number of fruit flies present at time t days after the fruit flies are released, will increase at the rate of 4.4% per day. She proposes that the situation is modelled by the formula n equals ak to the power of t. N is the number of fruit flies, t is the time t days after release. So part 1, we need to write down the values of a and k. So what do we know? We know when t equals 0, n equals 500. So that then tells us that 500 is equal to a multiplied by k to the power of 0. K to the 0 is 1, so this simply gives us a equals 500. So now let's have a look at the value of k. Well, they're proposing that the rate of increase is 4.4% per day. So really what they're telling us here is that k is going to equal 1.044, which is essentially the percentage multiplier for a 4.4% increase each day. Now, part 2, we need to assess whether the model is consistent with the value of n at t equals 10. So we're saying that n is equal to 500 multiplied by k, which is 1.044 to the power of t. So if we substitute in t equals 10, this then gives us a value for n, which is 769.086 ... which is 769 to 3 significant figures. The model is not consistent with the value of n at t equals 10 because we should have 650 fruit flies present at this time. So, part 3, what does the model suggest about the number of fruit flies in the long run? So, the model gives us n equals 500 multiplied by 1.044 to the power of t. As t approaches infinity, n approaches infinity. The model is basically suggesting there is exponential growth of the number of fruit flies. So we then refine this model, and subsequently it is found that for large values of t, the number of fruit flies in the controlled environment oscillates about 750. It is also found that as t increases, the oscillations decrease in magnitude. So Munira's second model is n equals 750 take away 250 multiplied by e to the negative 0.092t. Identify 3 ways in which this second model is consistent with the known data. So let's check out what the second model tells us happens when t equals 0, because we know that the value of n should be 500. So if t equals 0, n is equal to 750 minus 250 e to the power of 0. E to the 0 is obviously 1. 750 take away 250 is 500. So that's one way in which the model is consistent. We also know that when t equals 10, n is supposed to be 650. So let's substitute in t equals 10. So n equals 750 minus 250 e to the negative 0.92 when t equals 10. And this then gives us 650.37 ... which equals 650 to 3 significant figures. And what happens when t approaches infinity? Because we know that the number of fruit flies is meant to oscillate to around about 750. So when t approaches infinity, we know that e to the negative t will approach 0, which means that n will approach 750. So the model does actually predict the correct number of fruit flies for a long-term scenario. Now, 5 part A, identify one feature which is not accounted for by the second model. The model is supposed to demonstrate oscillation. We know that the number of fruit flies oscillates around 750, which means it might be a little bit above, might be a little bit below, but ultimately it's approaching 750. So the oscillations are not accounted for. Now for part B, give an example of a mathematical function which needs to be incorporated in the model to account for this feature. Well, you need to think about mathematical functions which allow for some kind of oscillation. Now, how can an oscillation occur? Well, an oscillation could be created by a trigonometric function. So if we use a sine or cosine function in our model, we will result in some kind of oscillatory behaviour.